Hi, we are Design Build Fly at the University of California, Los Angeles, and we are proud to present our aircraft patchwork.
A sensitivity study was performed to analyze the scoring parameters based on a preliminary design derived from reasonable assumptions based on past competitions. The parameters varied during the analysis were the velocities of mission 2 and 3, the sensor's weight and length, and the number of containers carried. The scoring analysis showed that increasing mission 2's speed has the greatest single effect on score, while increasing sensor weight and length is more energy effective. Carrying a single container yields an improved score due to the reduced loading time during the ground mission. The scoring analysis led to the conclusion that the aircraft should be designed to carry a single container with a long and heavy sensor.
Figure of merit charts were used to determine the aircraft configuration. These charts compare the performance metrics for each possible configuration and create a weighted score. The configuration with the highest score is selected. The following slides contain the figure of merit charts used to determine the final configuration of the aircraft. The chosen configuration is a monoplane with a high wing placement, a conventional tail, and a tricycle landing gear. Figure of merit charts were also used to determine the placement of the winch and the number of fins on the sensor.
An image of the sensor in addition to a table detailing sensor dimensions are shown on this slide. The sensor, shaped similarly to a rocket, has an outer diameter of 1.75 inches, cylindrical section of length 9.07 inches, and overall length of 15.17 inches.
The winch is rotated by a motor equipped with an encoder. The tow line connects the aircraft to an Arduino in the sensor, which controls the sensor lights. Our sensor container, pictured here, is a rectangular wooden case lined with a sponge. Drop tests verified the protective ability of the container. The sensor and container are stored in the same location below the wing. Sensor storage is shown in the bottom right. Note that 2 pins will latch the doors closed during Mission 2. The winch is mounted in the back of the aircraft, and the tow line runs from the winch through a pulley to the sensor.
Determined by a MATLAB code designed to deliver optimal dimensions given specific size constraints, the major aircraft dimensional parameters are shown on this slide. Tip-to-tail length is approximately 54 inches and the span is 59 inches. Other dimensions are included in this table. The gross weight of major configurations of the aircraft are shown on this slide. The empty weight of the plane without the battery system is 6.13 pounds. The lightest configuration is during Mission 1, when neither sensor nor container are loaded in the aircraft. The aircraft is flown in the heaviest configuration during Mission 2 with a gross weight of 11.33 pounds.
The elevator and rudder both span 33% of the chord and the full length of the vertical and horizontal stabilizer to give greater control authority when towing the sensor. The ailerons span 25% of the chord at the outer half of the wings. The wiring diagram for the aircraft shows the propulsion system, including the arming plug and fuses, as well as the receiver and servo systems that are powered independently by a receiver, switch, and battery. For the propulsion system layout, the single tractor configuration was chosen as it maximizes efficiency while minimizing weight and interference with the sensor mechanisms. An APC 12x12E propeller is used in missions 1 and 2 to maximize airspeed, while an APC 13x8E propeller is used in Mission 3 to maximize thrust and range. The other major components of the propulsion system include a 540 kV Cobra motor, 80 amp speed controller, and 2 6-cell 4,500 milliamp hour LiPo battery packs in parallel. Together, these components provide an optimal balance of performance, efficiency, and weight.
Here we detail our expectations for the mission performance of our aircraft. Missions 1 and 2 are expected to take about the same amount of time and result in similar energy draws, while Mission 3 is expected to require significantly more time and energy. We plan to fly Mission 2 with a single container and expect to complete 13 laps during Mission 3.
For a more comprehensive picture of our aircraft, here we have the 3 view generated from the CAD model, showing the plane with dimensions from the 3 normal directions along with the detailed isometric view. Later, we will compare this 3 view with the actual plane. You will see that the general layout of the aircraft matches the design.
We now present patchwork for visual comparison with the previously shown 3 view. We start with the isometric view of the aircraft. We now move to the left side view of the aircraft. Next, the top view of the aircraft is shown. Now we got the right side view of the aircraft. Last of all, we present the front view of the aircraft.
We follow with the demonstration of sensor deployment and functionality. The sensor is lowered out of the bottom of the fuselage. Note that in flight, aerodynamic forces will stabilize the sensor, keeping it oriented correctly. The sensor lights are now turned on, and the pattern of red, green, blue is displayed. The sensor is recovered by aligning with the fuselage and being pulled upwards until fully within the confines of the aircraft.
Next, we demonstrate the takeoff and landing of Patchwork in the Mission 1 configuration. Here is Patchwork taking off and entering stable flight. We will now fast forward through the flight to landing. This is the successful landing of the aircraft, described by our structures lead as, quote, like butter. Next, we view Patchwork flying in the Mission 3 configuration. Here, we see the sensor being successfully deployed in flight. With the sensor deployed, we see the aircraft in stable flight. The sensor lights can be seen flashing here in the same red, green, blue pattern as demonstrated in the ground mission portion of the video. Due to the video quality and sun location, these colors may not be distinguishable in the video. Unfortunately, due to the winch motor failure, we were unable to retract the sensor into the plane during flight. Luckily, both the aircraft and sensor survived the landing and remains functional and ready to fly again in the near future. Design Build Fly at UCLA thanks you for watching our competition video.